welcome to another screencast. This time we're going to talk briefly about velocity fields. Now, what's a velocity field? Well, a velocity field is a vector field, of course, but we're interpreting the velocity at the vector at each point as the velocity of some moving particle. So we're going to imagine a particle moving in our space, so x and y will both depend on t, and then we want to figure out a path where the value of the vector field is the velocity of that particle. Right. So the goal here is to, given a vector field f, find a path, find functions x and y, so that given an initial point, right, so you know the position of your particle at some point, you want to know where it's going to go, what's going to happen to it. So let's solve for x of t and y of t. This is a bit ambitious. This is a system of ordinary differential equations, right? There's a whole course essentially on these guys, and so they're generally, to solve them exactly, is not easy. That's the bad news. The good news, though, comes when we think about our position as being a vector valued function here. And then we've got a theory for approximating values of these guys, right? If we know the value of our function, our position at a time t naught, right, well then a little bit later, say t naught plus delta t, we know our position is approximately that position plus the derivative at that time times delta t. Right? And for our vector field, we know what that is too. Right? We've got the initial position and we've got the value of the vector field there. Right? So this is just a simple application of linearization that lets us approximate where our particle is going to go given any starting point. Let's do a quick example. So here we've got a particle which at time t equals 1 is at position 1, 3, right in the middle of our plot here, and it's going to move in the velocity field xy minus 2, gamma y squared minus 10. And solving that nonlinear system of ODEs would not be a lot of fun, but you can see intuitively what's happening here. We've got a particle located at 1, 3, and it's going to just follow this vector field. At every point, its velocity is given by this vector field. Mathematica has put here what's called a stream plot, so you can really see kind of the lines where the solutions to this ODE are. So approximating that value a little bit later, time t 1.05 is straightforward. We know that we've got an initial position at 1, 3 at time 1. To find the velocity there, we just evaluate our vector field at 1, 3. It's that simple. Plug in 1 for x and 3 for y. We get 3 minus 2, and we easily get 1 minus 1. We look back at our plot. That looks accurate. We have 1 minus 1 being the tangent vector there. And from there, it's just linearization. So our value at 1.05 is approximately the initial value, 1, 3, plus that delta t. So remember, the change is just 0.05 here, times the velocity, 1.01, 1.05, 2.95. Simple as that.